Hello, everybody. Welcome back to another discussion in dynamics. Today, we'll just do work energy methods for system of particles, okay? And let me start with a brief lecture review. So yesterday in the lecture, Professor Sani told you that work of internal forces is 0 when objects do not move relatively to one another. Yes, so for example, work of inaccessible ropes is 0. However, if the objects do move relatively to each other, for example, when they slide on one another, then that work is not 0. Yeah, we will have some dissipation due to friction, for example. Yes, okay, that's it. That's the gist of yesterday's lecture. Yep. And today we will do example number 1 and example number 2, and I think that example number 3 you will just have to watch the video on YouTube. Okay, I managed to do example number 3 last discussion. Okay, but I think that right now we are not going to have time. Yeah, so just go to our channel, or I will actually send you a link. I will send you a link via email. And now you can, if you want, you can tell me what you think about my discussions. Okay, so you should probably receive an email. Or just go to that website and just fill out the. Just let me know what you think about these discussions. Yes, and you have time till Sunday, this Sunday. So I will just remind you about that on Friday again. Okay. And by the way, how many people do we have in here? Okay, we have 40 people. Okay, so statistically speaking, we have 4 haters. Okay, 4 of you hate me. Like really, they think that I'm the worst person ever, and they are gonna fill out that survey. Okay, so if you guys think that I'm a good guy, if you like it, please go and fill it out. Okay, because I must tell you that haters gonna hate. Those haters will go there and they will say like some mean stuff about me. However, to be honest, I have never read any meaningful bad comment about myself. I honestly don't listen to you guys. Yes, you can write whatever you want. Yeah, but it's also always nice to see like a nice thing about you. Yes, yeah. So once I remember one semester, only like 5 people took that survey. Yes, I got like 40 people, only 5 took them. 3 of them were haters. So I think that picture of me was a little bit distorted there. Yeah. So just in case, so I just want them to be outnumbered. Okay. Yeah. But it is just voluntarily, yeah. Just if you don't want to do it, don't do it. It's fine. Yeah. Okay. So what? Example number 1. So it looks like Taylor Swift was right. Yes. Haters gonna hate. Really, yeah. Okay. As usually, you know what to do. Yeah. As usually, please familiarize yourself with the problem statement before we start our solution. All right. So what do we have in here? We have 2 bodies. Yeah. We have a little body and big body. Little body has mass lowercase m. Big body has mass uppercase m. And little body will start sliding on the big body. Yeah. We have no friction between big body and the ground. This surface has no friction. And we have a friction, yeah, between these 2 surfaces. And we know the velocity initial of little body. So then, once the little body starts sliding, this velocity will start decreasing, but this velocity will start increasing, yeah, until they reach exactly the same value. and they ask us to find, they ask us to find where the little body will stop. Yeah, they ask us to find this distance. Questions? Let's do it. So let's solve it. Okay. So I'm not going to surprise you with the first step. Yes. First step will be T1 plus V1 plus U12 non-conservative. This is equal to T2 plus V2. Okay. Second step, just find these 5 things. T1, V1, T2, V2, U12 non-conservative. All right. So I'm just going to fill them out. So at the beginning, and by the way, subscript 1 corresponds to configuration A. Config A, which is this configuration. And subscript 2 corresponds to this configuration, config C. All right, so what kinetic energy do we have at the beginning? Only one body is moving, yes? Only one body. So we'll have 1/2 little m V0 squared. And that's all. How about at configuration C? We will have two bodies moving, yeah? We will have 1/2 little m V final squared plus 1/2 big M V final squared. Okay, how about potential energies? So V1 and V2. Do we have any springs in the system? No. Do our bodies change their elevation? No. Okay, 0 and 0. No springs in the system, bodies don't change elevation, potential energy is 0. Okay, how about U12 non-conservative? We have a friction in our system, yes? We have a friction, so it will be work of friction here. Work of friction. So that would be TF with negative sign times distance. Yes? And what distance should I put here? Yeah, that delta rel, yeah, D, yeah, delta rel. Yeah, this is the relative sliding distance between two bodies, yeah? And let's just very quickly find TF. So, and you guys probably know that TF will be equal to mu k mg. Yeah, let's do it quickly. FBD for just little mass. So we have mg, we have n between two bodies, and we have TF in here. Yeah. By the way, n is also a non-conservative force, yes? But you guys know that work of n will be 0. Yeah, because this is our trajectory. So you can see clearly that n is perpendicular to our ds. So, and since this is our trajectory, you can clearly see that n minus mg will be 0. So n is equal to mg. All right, so this is equal to minus mu k mg delta rel. Great, so we solved 100% of the problem, yes? 100% done. So let's plug in these these 5 guys back into our original equation, yes? Because that was our next step. So we should write 1/2 m v0 squared minus mu k mg delta rel is equal to 1/2 m plus m v final squared. And this is one equation, one unknown. So just you can find that, just plug in values, grab your calculators, and obtain that our delta rel is approximately 6.95155 feet. This is the answer. Questions to what happened so far? By the way, this time we have homework 6, yeah? Like this week is like homework 6 or 5, I don't remember. This is actually example number 1 on that homework. This is example number 1. So you have extra points on homework, okay? But 5 other problems do without social manuals, okay? Any questions? So maybe this problem. Please familiarize yourself with the problem statement before we start our solution. All right, so what do we have in here? Again, we have two bodies, yeah? We have two bodies. Oh, Ian, do you remember? Like 2 weeks ago, you asked me about shall we consider only two bodies separately, or can we like consider a system as a whole? Yeah, that was your question. I remember. So for kinetics, yeah. So the previous chapter, yes, each body separately. Free body diagram, you should draw for each body separately. Work energy method allows us to consider system as a whole. Okay, so this is the answer to your question from 2 weeks ago. Okay, so we have two bodies, yeah, and they have exactly the same mass, yeah. We have body 2 in here and body 1 in here. And there is also a linear spring of spring constant K attached to body 1, and we have friction between body 1 and the ground. And two bodies are connected by a rope. And what happened to our system? This guy, body number 2, was pulled down by 2 feet. Yep. This guy went down by 2 feet, so that means that this guy went to the right by 1 feet. Yeah. So we have some preload in our spring. And we are just asked what will happen, what will be the velocities of two bodies once this guy rebounces back, yeah, when that guy goes up by 1 feet. Okay, and the system is released from rest, of course. Questions? Okay, so let's continue our routine, okay? I'm not going to surprise you guys, yeah, if I write that equation. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. T1, V1, T2, V2, U12 non-conservative. Okay, system starts from rest. Yep. So I solved 20% of the problem. Okay. And by the way, subscript 1 corresponds to config A, which is this configuration, and subscript 2 corresponds to config B, which is this configuration. So at config B, I think two bodies have velocities. Yes, so I can write in here 1/2 m v1 squared plus 1/2 m v of body 2 squared. Okay. So we have two unknowns in here, v1 and v2. Oops. But there is a relationship between them, yeah? Maybe some of you can tell me. Where should I put number 2? So v1 is equal to v2. So I should put number 2 in here or number 2 in here. Why number 2? Because we have one rope attached in here, yep, and two ropes attached in here. So I should put 2 in here or 2 in here. v1 equals to 2v2. Okay, one more guess. Take one more guess. Great, here. Yes, that's good. That's great. Yeah, yes, because even look at the lengths of these vectors. Yes, v2 is larger than v1. Yeah, even this is a hint. And I usually figure that out following this like approach. So I know that if I pull this guy down by 2 feet, this guy will just go to the right by 1 feet. Yeah, because it has two strings attached to it. And that's how I know. Yeah. Yeah. But I think that person who was wrong, maybe I just forgot to define which body is 1 and which body is 2. Yeah, probably that was the cause of the mistake. Anyway, so this is body 2. This is body 1. Okay, anyway, now potential energy. Do we have springs in the system? Yes. We have our bodies change elevations? They do. Okay, so let's write in here V1 gravity plus V1 spring. Okay, and I already put datum here. Yeah, our datum is here. So I believe that V1 gravity will be mg minus 2. Yeah, because only body 2 changes elevation and it is 2 feet below our datum. And when it comes to spring, spring is stretched by 1 feet. So I can write in here 1/2 k1 squared. Yep. And when it comes to V2, we will have the same division, V1 due to gravity, oh sorry, V2 due to gravity plus V2 due to spring. And okay, so this is elevation of body 2 right now, mg minus 1, and that spring is stretched by 1/2 feet. So it will be 1/2 k 0.5 squared. Okay. So we have 80% of the problem done. So let's do 100%. But before that, any questions? I have a question. There is a transfer student. So there is like a student who switched discussion to mine. Are you here? Oh, you're there. Okay. Okay. We can talk after the discussion. Okay. Yeah. Lars? Yeah. So please don't write it. Yeah. I'm just gonna So let's assume that so just these values will change. These values will change. This and this. Okay? So if you want me to put datum here, that means that 0 will be here. Yeah. And 1 will be here. Yeah. And the solution will be exactly the same. If you don't believe me, try it at home. Okay? However, I'm gonna go back to what was there before. So I'm just gonna operate in these values. Okay? But if you put datum there, your solution will be exactly the same. I mean, the answer will be exactly the same. Okay. Any questions? Any other questions? All right. So let's do 100% of that problem. Do we have friction? We have a friction in the system, yes. So we have to put it in here, yes. Work of friction. Okay, but let's put it in even more mathematical form. So it'll be TF, work of TF. Okay. So I will just draw FBD for body 1, okay? So what forces act on our body? What forces act on our body? We have mg, we have n, which is also non-conservative force, okay? We can also put there n. We have tf, no, sorry, not this way. This way, yes. TF acts this way, no, this way, good. And we also have kx. But only 2 of them are non-conservative, yes? Only TF and N are non-conservative. So, sorry guys, I will just erase this thing very quickly. I hope you won't hate me. And I will put work of N for the final time this semester, okay? By the way, in this semester, work of reaction forces is always 0. I bet so, yeah. Work of reaction forces, no, actually not, because there can be like a rust or something. Yeah. So 99% of the time, work of reaction forces is 0 because they are so-called smooth constraints. Okay, smooth constraints. Doesn't matter what it is. Yeah, Calvin, not Calvin. Trevor. Is there a tension on that one? Oh, there is a tension. You're right. Okay, so I made a mistake. Thank you. 2T. But we know that work of internal forces is 0. Yes, remember lecture? Yeah. So we will also neglect 2T. Okay. Anyway, you have U12 of TF plus U12 of N. It's only red forces, non-conservative forces. So you will have in here this guy will be minus TF. Oh shoot, minus TF times this distance times half a feet, yeah? And this guy will be integral from A to B for the last time this semester, okay? N times ds, and you guys know that this is 0. Yeah, this is 0 because N is perpendicular to ds. Because this is our trajectory, and this is our ds. Great, and TF is equal to mu k N, where N is equal to mg. So we can clearly see that our U1 non-conservative is equal to minus mu k mg 0.5. Okay. Any questions? So it seems to me that we have 100% of the problem done. Yes, the last step is just plugging in everything back into our original equation. However, these expressions are long, so we can actually grab our calculator and figure out what their values are. Okay, so value of T1 is the simplest to calculate because it's 0. Value of V1, if you plug in values here, you will see that V1 is exactly 30 joules. Value of T2 has to be 5 divided by 2 mv V1 squared. Value of V2 is equal to 2.5 joules. And U12 non-conservative, if you plug in values and grab your calculator, will be minus 1 joule. Check this out. Now we can plug everything back into our original equation. And we will end up with 0 plus 30 minus 1 is equal to 5 divided by 2 mv squared plus 2.5. One equation and one unknown. And that unknown is not v, but v1 actually. v1. So let's find v1. v1 is approximately 5.842 feet per second. And they also asked us to find v2. v2 is equal to 2v1. And this is approximately 11.685 feet per second. This is the answer. Okay, questions? No. Okay, so just closing remarks. Do you see that there is like a recipe to solve this problem? This type of problems, yes? So just follow that, just get familiar with that recipe, do homework following that recipe, and you're ready for the exam. Yeah, when it comes to this. And one more thing, make sure to enjoy your afternoon, okay? Yeah, bye.